Okay, in this video, we're going to explore Egret a little bit more. We're going to introduce LIN movements, PTP movements, and this component I have built for Egret itself, it's called Path Curve. We're going to go through each one of them quite quickly. But first, I can just show you the generated toolpath I made over there. I loaded up into the Python IDE of the UFactories itself, and we just can run it over here, and you'll see it on the video here. So this is going to run a LIN curve first, and then a PTP curve, and then finally the the curve component I made for Grasshopper. When would you use each one? Well, PTP will get you there the fastest, but it doesn't really consider the joints, angles, and all that, and may blend curves and whatnot. Whereas LIN movements is a linear movement. It's going to be as close as possible to that intended curve as possible. And the PCV component, that just takes an existing curve made in Grasshopper and does a lot of the framing of it, the flipping the normals, and gets prepared for the robot itself. But we'll go through each one individually. So you saw on the left, the robot played through all three of those paths. So let's go ahead and just kind of rebuild this, and we'll step through it one at a time. Let's go ahead and delete all this. Remember, we want to drop in our robot first. So let's go to robots, and let's just drop in robot. Again, I'm using the Lite 6. You can be in a X5 or X6 or 7, or the 850. So we have our robot that will be inherited across the canvas. And next, let's drag in a curve component. So this is the curve we want to trace or have the robot follow. Right now, it's not assigned to a curve. In fact, I'm just going to undo everything real quick. I have my curve internalized, so I'm just going to delete all this. And now we're back to where we just were. But you can see my curve, I just have a random curve I generated inside of Grasshopper. I'm sorry, inside of Rhino, and made it in Grasshopper. If you open up this canvas, the curve will be internalized inside the GH file. So if you want to reuse my curve, you can. So let's go ahead and start building out the framework that we keep using over and over and over. We need a robot, and we need the stage, which interprets toolpathing into code. I'll go ahead and make a panel. I will drag in there. It shouldn't have anything in there. Yep. Cool. So what's the first thing we want to do? Let's just go ahead and use the path curve, which is underneath the toolpath. It just automatically takes the curve, turns it into toolpathing. You can see the LIN commands already there. We can adjust different things, such as dividing the curve based on distance. So if it's on 100 meters or 100 millimeters and you divide it by 5, you get 20 reference points. If you want to have a very smooth curve, like smaller intervals, you can increase that up and down. We haven't learned about tool planes yet, but we're going to just assume it's XY plane for this. Speed, you'll see us again and again. I'm going to keep it at 50% speed. I think that video you just saw was at 50% speed. And then the robot is the Lite 6. So right off the bat, we can just drag this T into stage. And you can kind of see what the URDF skeleton looks like. We can switch this to real to emulate the real robot. Awesome. If I haven't showed you yet already, you see this time interval. We can make a number slider and just say 0 to 1.00000, or more zeros if you want. And that we can play back the motion with the robot. So that is my curve, and I'm staying parallel, or I'm playing parallel to the XY plane. We could change the pose to that, but for this, we're just saying parallel to the XY frame. If we wanted to make code just for this line, we can go to our output and get code. Drop our T into here. And there you go. You have the toolpath code for your robot to run that path we just simulated on the left. That curve. If you want if you want G code instead, let's go ahead, hit G code. And that will also follow the same exact line. While you may not always have curves, maybe you have like a pick and place, you'll be dealing with planes. So we can do the curve and treat it as planes, which is probably what most people will do. Let's go ahead and divide this curve using, just a divide curve. I'm going to make it 10 samples. I think that's default. Yep. So we need to make a plane, an XY plane at each of these points. We can just use the native component XY. And now we have planes at each one. So if we want to tell the robot to go from each plane in a linear movement, we'll go to targets, hit lin, put P, and then drag it into here. You're going to notice I have some errors, and you can see we have some tool issues. It says inverse-kinematics failed. Essentially, it can't solve this path. Well, let's figure out why. I'm going to see which way these planes are pointing. I'm going to type in SDL, start distance line. I'm going to drag my origin there. The direction. I'm sorry, SDL. It's start direction length. Direction, we'll just make it Z up, and the length, it doesn't matter, 100. So what I can see right here is the direction of my plane is opposite of what my end effector is at. So the robot is trying to rotate underneath it and solve as if the face or the end effector is pointing in the Z positive direction. That's not what we want. So how we can fix this is just using a flip plane command. Flip plane. Awesome. And now the robot will follow that line. I'm going to turn off my SDL line. And then we can also emulate this again. If you wanted to make a PTP, just type in PTP. Or you can grab it from the targets command and have PTP there as well. If you wanted to run all of them in parallel, well, in series, we can use a merge command. This is what I showed in the video. So it will do the lin movement first, and then it will use the PTP movement, and then finally the PCV movement. And we can play through each one. I don't know if I've shown it yet in the previous videos, but I'll show you again. If you double click stage, you can see where any singularities may be or warnings. And if you just want to play this versus trying to use the number slider, we can just play this on repeat. You see there's some different speeds, and you can change those inside of PTP speeds, or the LIN speed, or in the PCV speed. So one thing to note when you're making these lines or toolpaths is the point density. So right now, this is 125 points to do those curves. So what is the first curve? It has 11 points, 11, and the PCV has 103. This is because it's dividing up your curve a lot. It's going to try sticking as close to that path as possible. But it's also going to move a little bit slower, but it's going to be the most accurate. We could make the LIN and PTP more accurate by cranking up how much this is divided. Like so, we can just make this 100 points. And you can see now I have 100 planes. And I kind of misspoke saying this would be the most accurate. This is just dividing the curve by 5 millimeters, whereas this one, this top two, we're dividing the curve into equal parts, 10 parts. But you'll see now that this is 101, it's 103. It's just coincidence that they're so close. But do we really need all those points? So if we had a straight line and we said divided by 10, we don't really care about the 8 points in between. We just need to know the start and the end position, and we don't need to like cumbersome the controller with all the in between points. There is an option to use a reduce path. It's also in the toolpath and hitting reduce. We could drag this into here, and you can see our toolpath did reduce a little bit by a third, and it should have the same curve. Sure, there's going to be some deviation. You can see I have a 0.2 millimeter deviation in the line, in the path, but I reduced the tool pathing I dropped it 200 points. Or I dropped it to, it's 1/3 of what it was. So, you can play that up. If I cranked up this tolerance, it would start increasing more and more points. And, it would play out that way. I'm going to stop the video here. I'm going to publish this GH in video, and we'll start moving on to the next tutorial.